All right, so today we are going to talk about light and matter. We're going to talk about photons. So there was there was a numerical homework due today, but I kind of talked about it on Friday. So I can talk about it again if you want, or if you have questions about it, you can email me. I'll put all the solutions up in the next day or two so that you can take a look at about how it's supposed to look. But I'm not going to worry too much about that anymore today. So I'm going to finish up with filters and color, which I hadn't quite gotten all the way through, and then I'll talk about photons and quantum mechanics, which underpins a whole bunch of what we do. We don't need to talk about the details of quantum mechanics too in depth, but because we don't have that kind of time. But we do need to talk a little bit about it. So I'm going to go backwards through the readings because there's a couple of questions that I think I didn't answer yet that I'm going to real quick run over before I get to new stuff. So let's start with 4 here. So how is magnitude related to the inverse square law? So this is, I want to make sure that I spend a second with this because it's important. So we have 2 different magnitudes that we deal with a lot. And I'll show you another one today, but there are 2 magnitudes that really matter. Apparent. Are there 2 P's in apparent?
Yeah.
Yes.
I have no idea.
We have apparent and absolute. And this one's little m and this one's big M. And they look like the same thing and they smell like the same thing, but they're actually vastly different things. Because one is a thing that I measure and another is a thing that I compute from physics. And they're related to each other by the distance modulus mu. Mu is the difference between big M and little m. And it's equal to 5 times the log 10 of the distance between them in units of 10 parsecs. So this is the way magnitudes and the inverse square law are related. Now, I don't see an inverse square in there. It's in there. Where's the inverse square? It's this d, but that's not inverse or square. Well, okay, I've got a 5 out here, and when I define a magnitude, we define it as m1 minus m2 equals minus 2.5 times the log base 10 of the ratio of the fluxes. And this definition will get you to whatever else we're talking about, but the log of the fluxes has the inverse square on it, and because there's a minus 2, the minus 2 comes down out from the log and turns this minus 2.5 into a plus 5. So that's the relationship. And that's how we use magnitudes to find distances. So big M, I can compute from a black body. And that's what part of the homework is on. There's a homework that I put up this morning. It's due Friday. Normally I try to give everybody a whole weekend to do a homework, but it's not super long. I don't know how hard it is. You'll have to tell me. But it's only 6 questions, maybe it's 7. But it's not as long as the last one. So due Friday. If anybody has any serious constraints, let me know. Yeah.
You put the wrong date in Canvas.
Oh, really?
You put the 7th of this month.
Oh, did I?
Which is already passed a while ago.
No way, cool. Okay, can you email me that? Because I'm totally going to forget.
Okay.
Do this Friday.
Can do.
Yeah, so do this Friday. Office hours on Thursday. Sorry about the date. That clearly doesn't make any sense. So you'll do this, and you'll compute the absolute magnitude, and you'll play around with black bodies a little bit. And you'll do some of the math that I threatened you with. There's a couple of times I said you're going to see this for homework, and that's some of those show up. So you will see that again. How do you use this to get to the distance of the star? Same thing. Why is radiant flux important? Radiant flux tells us how much we're getting. It tells us the total net contribution from photons that we're receiving. So it's the most important thing. Why is it u minus b and b minus v? I'll show you this in a second. And not, so I'm gonna show you 3 filters. And they look like this, u, b, v, I, and then the u, b, v, I. and this is a flux, and this is a wavelength. You usually use filters that are next to each other in wavelength space because we're often turning these things into derivatives. So do you remember what a derivative is? I mean that in a little bit of a sarcastic way, but also in a very specific way. What's a derivative? A derivative is delta f over delta x as delta x goes to 0, right? That delta x goes to 0 is important. You need, so when I want the slope of a line, it's rise over run, I need the rise bits close to each other and the run bits close to each other. So I want the spectral bands close to each other too, because I'm going to turn them into derivatives. I'll explain that more later. But that's why. And the combinations are always such that a lower number is more blue. They're always in that direction. So a lower number has more contributions from short wavelengths. All of the colors are defined that way. Let's see. Why 10 parsecs? I'm not sure. Will we review main sequence stars? Yes. We'll do that in a second. Well, I got to talk about the insides of stars first. Propagation is just moving. And how does light affect the color index of a star? So the color index of a star is, I'll define this later. It'll make more sense maybe after I define it. It's just the ratio of how much light I get in two different wavelengths. So light is the color index, so that's what gets it the color index. And color diagrams, are they related to color magnitude diagrams? They are, but they don't give you distance information, or they're not confused by distance information, so they're kind of more awesome. I'll explain that again later. So some of those things I'll fill in today. Okay, a couple of quick questions from reading 5. In Rayleigh's derivation, what determines short and long wavelength? This is an important question. So this is an important question because you're going to be asked to do this on the homework. So I ask you to take the Taylor series. Don't worry, it's not too bad, and I hand you what the Taylor series is a problem. But how do I know what's short and what's long? There's a thing that looks like e to the hc over lambda kt. And this is the Boltzmann factor, and it tells you how much of a thing you get. Oh, sorry, forgot a sign. It tells you how much. It tells you what the probability is of having a thing with this energy, but this quantity defines what long means. So if this quantity in the exponent, hc over lambda kt, is big compared to 1, then that's a long wavelength. Does that make sense? Or small compared to 1. So we've got hc over lambda kt. That's a number, that's a number, and that's a number. That's the only thing that really matters. But if this is much, much larger than 1, then lambda is small. It's upside down, right? So if 1 over that is bigger than 1, then we consider lambda small. And the opposite, if it's much, much bigger than 1, then we consider, or if it's much, much smaller than 1, then we consider lambda large. So it's relative to this other combination, HCKT, which gives you some other kind of wavelength, but I don't know what that is. Maybe there's something interesting there, but I don't know. How did Planck come up with this? Did he just plug stuff in? No. There's a derivation that you'll see when you get to statistical mechanics. You can derive this Planck function from first principles. There's no guessing or hand waving or making stuff up. There's just a couple assumptions and some counting, and then it comes out. It's hairier than what I feel like getting into, and you have to set up partition functions and stuff. So you need a little bit more machinery than what I have, but it's very elegant. It's really cool. Let's see. There's an integral that gives us the monochromatic luminosity. How is that different from the bolometric luminosity? So the monochromatic luminosity that the book defines, he gets it this way. I say he, but it's a they. And it's a they as in two people, not one person. But I'm going to continue using he because it's easier that way. Oh, yeah. So he defines this thing that he calls that he calls the monochromatic flux. And it is the black body integrated over area and integrated over solid angle. And there's a cosine in here for that solid angle, for the projection. This is what he defines as the monochromatic flux. So this means just frequency information, no geometry information. So we've integrated out all the geometry information. So we're only looking at frequency information. Then the bolometric luminosity, can somebody say what they think the bolometric luminosity is? How would I get the bolometric luminosity from this? Not a derivative. Bolometric means all of it. Yeah, I integrate. I don't need to do the 1 over, I just need the integral part. So it's like an average, but without dividing by. So we just add everything up. So I take this monochromatic flux, I add it all up, and that gets me my bolometric flux. That's on the homework too. So add it up. Integrals are just adding things up. Averaging is just adding things up too. So averaging and integrating are super related processes. And a lot of times, anyway, I had this, I'm writing this paper about outer space because that's what I do. And I ran into this problem where my numbers weren't coming out right because I'm comparing what the turbulence community does with what the cosmic microwave background people do. And they define things differently. And I've been working with this for like years, and it just became clear that they define their averages differently, so they get totally different answers. So you got to be careful with averages. Okay. Why can't we get rid of H? Did any of you play Undertale?
She's going through her Undertale
All right.
phase right now.
Oh, are you really? All right.
I'm drawing Undertale on my phone as you are talking.
Okay, so in this game, one of my favorite things in this game, I didn't play it, but my kids did, and I heard all about it. There's this thing called dog residue that you accidentally pick up, and everything, and your whole inventory slowly gets filled with this stuff called dog residue, which is
dog residue.
which is one of the funniest jokes. There's lots of hilarious jokes in this game, but anyway, H bar is the dog residue of quantum mechanics. You can't get around it because everything is quantized at about the scale of H, because that's how nature works. So you can't really get around H when you're dealing with quantum mechanics because it's kind of glued to everything, kind of like you stepped in something. So as long as it's quantum mechanical, there's going to be an H. And figure 3.9. Okay, so I didn't spend a moment with this figure, but let me do that now because you're going to need it maybe. So there's this figure that is this coordinate system. And there's a little blob, and there's a theta here, and a phi here, and an r here, and a bunch of d's around here. And what this is doing, what this graphic is doing, is demonstrating where the angles are, because when you're in spherical coordinates, you got two angles. You got an angle that comes down from the pole, and an angle that goes around, and they're different. The one that comes down from the pole, the elements are small up here and they get bigger as you go down from the pole, so there's some dependence on that. And it only goes from 0 to pi, but the other one goes from 0 to 2 pi and there's no dependence on the angle side. So this graphic is really to orient you before you do the integral, but it also shows you how the volume element changes with space. So if this little wedgy Q here is the volume element, you can see as I slide it outwards on R, it's going to get bigger like R squared. And if I move it up this way, it gets smaller like theta. So this graphic is really to orient you. If anybody wants to talk about that graphic, it's really best to do it in office hours or email me specific questions because it's kind of a lot to get your head around this picture. And Somebody asked, can I go over the spherical coordinate systems and how they relate to RA and DEC? So it's very similar. We just have a polar coordinate system that's along the axis. The up from the equator is the declination, and around from the pole is the right ascension. And the 0 of the right ascension is defined at the vernal equinox, which we just passed. Happy fall, everybody. Okay. How long have I been talking? 12 minutes, okay. Okay, so questions from reading 6 and 7. Oh, sorry, just reading 6. I forgot to look at reading 7. Nice, sorry. I'm only realizing that now that there was a thing that I needed to go look at that I didn't do. So why is Compton important? Compton is important because it shows that photons can change energy. And there's this weird formula that all that says, I'll explain this in a second, all that says is momentum and energy are simultaneously conserved. So if you're going to change the energy of a photon, you have to change its direction too, because otherwise you can't solve the system. I'll explain that in a second. So Compton is important historically, but also when we're dealing with an astrophysical system, Compton scattered photons show up as distortions to our spectrum. So we need to understand Compton. But not right now. We don't really need to worry too much about it. I'm not going to ask you to do any Compton scattering things. That's what modern's for. What is h bar? So h is the quanta of angular momentum. H bar is the quanta of angular momentum. Does that make sense? So the universe gives us angular momenta in units of h bars, just like the universe gives us candy in the form of Tic Tacs. I can have a huge pile of Tic Tacs and eat them by the fistful, but they're very little things. Just like angular momentum, I can spin around all day, but it's in units of h bar.
So it's the smallest angular momentum that particle that can have?
If it's got angular momentum, yes. It could have 0. But that is a thing. That is another thing that it could have. So it can have.
It can only have 0 or that or more.
You can have 0 or some of these or some number of those. Some number of h bars. So n times h bar. So it could be 0 or some of those.
Can it have between 0 and 1 h bars?
No. You cannot have half an h bar. And that's important. That's a really important thing, is you can't, if you're spinning around, you can't spin half as fast. You have to go down the whole next level. I'll talk about that more in a second. Why is photoelectric relevant here? So photoelectric effect doesn't show up in outer space all that often. It does if you're looking at the interstellar medium, because there's these grains of dust that kick off electrons from UV photons. We really talk about it here because we need to talk about quantum mechanics, and that's an important part of the quantum mechanics. So I need you to know what photoelectric is and basically how to use it, just because it's energy. It's really straightforward. What does it mean to ionize an atom? That means to take electrons off of it. So a neutral atom has the same number of protons and electrons. And if I take an electron off, then I have an ionized atom. But I have to take the electron all the way off. I can't just excite it. So I have this energy structure for my hydrogen atom. It can be anywhere in there. As long as there's an electron on there, then it's an excited atom, but it's not ionized. What are the principal quantum numbers? The principal quantum numbers are the quantum numbers that describe the system, and they change from system to system, but they're the important quantum numbers. Where does Bohr's model fail? Well, for the electron, it actually works great. It starts to get fuzzy when we get more protons and more electrons. So Bohr works great for hydrogen. It works great for helium if it's missing an electron, because then it's just a big nucleus, but there's only one electron. But the electrons get in the way. And I'll talk about this in a second, but the other electrons make the model break down, and you have to use fancier approximations. But the basic physics is pretty solid. Do we treat photons as particles or waves? More often, and we use the thing that we need at the time. There isn't one that's prevalent, because sometimes it's quantized and sometimes it'll bend. There isn't an or there. There was only really an or back before they really had quantum mechanics. I have no problem with something being simultaneously quantized in a chunk and having wave properties. So we do both at the same time.
More than one of you got lost in the Bohr atom. That's cool. I'll hook you up. Where are the electrons in the Bohr atom? I'll show you in a second. I will discuss the Balmer series and all those other series when I get there. Why does emission in spectroscopy use the air speed of light, not the vacuum speed of light? Usually because the spectrograph is in air. So most spectrographs are in normal atmosphere. Are the energy levels of electrons the only thing capable of determining the energy of photons? No. If I take one electron and I jiggle it, that doesn't have any energy levels. That's just it moving around. That'll radiate photons. Or if I take a proton and I radiate it, or if I take, so there's lots of ways you can get photons other than quantized chunks. Can photons be created through other means other than this level descending business? Yes, all kinds of places. We'll talk about some of them. Why do photons not interact with each other? That is not accurate. They do. I could take two photons and smash them into each other, and if the photons have enough energy, I can make an electron and a positron. And that kind of thing happens. There's a kind of star called a pair production supernova that we think probably exists, but it's when the interior gets so hot that the mean photon energy is high enough to create positrons and electrons. So just from having photons smashing into each other, you get positrons. How do you get elements from spectra? I'll talk about that. That's what lines are for. And what is phi in the work function? Phi is the amount of energy that you need to take an electron off. I'll explain that more in a minute when I get there. Okay. So those are the questions that I wanted to quick touch on. Does anybody have any other questions or questions about the questions? Or questions about the questions about the questions? Yeah.
Well, I just one quick question. So about the photon stuff, because it mentioned it in the reading for like a sentence, but how do they have momentum if they're massless?
They have momentum.
Right. How do they? Oh, is it? Okay.
I have no good answer for that, to be honest.
It's okay.
Everything has momentum because they're moving, but you need to think about momentum as just a property that the photon has, and the photon momentum is just E over c, which is kind of simple. Yeah.
With the distance modulus, is it -5 log?
No, 5 is positive.
5 is positive, okay.
Yeah.
Just making
The
sure.
more stuff that you couldn't read wasn't perchance in funky colors on sticky notes.
Some of them, yes.
Oh, that was probably me then.
No, not just you. There were several people. I super don't mean to call anybody out in public on their handwriting, but
No, I know
some of you
it's-
have bad handwriting. I also have bad handwriting, so I don't mean that in a judgy way. But if you could be careful with your questions, that's easier for me. The rest of it I can kind of guess at to the level that I need, but the questions I need to be able to read.
Okay.
Okay, I'm going to give you one super useful thing that I did not realize you could do it this way until I was writing the homework set. This makes so much more sense, but I can't define it this way because that makes everything really confusing. But the absolute magnitude, what is the absolute magnitude? It's the magnitude as though the star, or whatever, we'll just use stars for now because that's all we're going to deal with. It's the magnitude that one experiences as though the star were at 10 parsecs. And, let me write it up here. M1 minus M2 equals minus 2.5 times the log base 10 of F1 over F2. Okay, so all of this has some baggage with it. But if I do that and I make M1 the absolute magnitude and M2 the apparent magnitude, and then F is the flux, and F2 is all of the other crap that I need for defining my star, then I get the absolute magnitude is just the luminosity, which you can compute from physics, divided by this fiducial number that happens to be 3.0123 times 10 to the 28 watts, or 10 to the 35 ergs. So if you need to know the absolute magnitude, you plug it into here. You're going to need that for the homework, which was a great revelation because the way I was doing it before was so much grosser. This is so much nicer. So if you need the absolute magnitude, it's just the ratio of
the actual luminosity to this fiducial luminosity. And this fiducial luminosity, where does this come from? It is the luminosity of an A star at 10 parsecs. And somebody very thoughtfully computed that and worked this out. And there's some definitions where things are supposed to be close to 0, but they're not quite, and it's all a little hairy. But this is what you need. So then, if I give you the apparent brightness, you can get the distance. Or if I give you the distance, you can get the apparent brightness. But the absolute brightness you get from physics, and the apparent brightness you get from a telescope. Those are the important differences. But start here. I was sitting down to write the homeworks, and I was like, okay, how do you do this problem? How did he do this problem? Oh, that's a much better solution. So I learned something really super useful. This is tighter. Okay, so we define magnitudes this way. And for the apparent magnitude, M1 is what I measure with my telescope. M2 is what I measure with my telescope for Vega, or a fiducial star. So this is what I compare everything against because I take the log. And so F1 is the flux that I measure, and F2 is the flux that I measure from Vega. So that's another fiducial thing. So you don't actually have to measure this with your telescope. That's just the way they set it up, because back in the day, it was much easier to do things that way. You had a lot more variations back in the 1800s when you were taking pictures of things on silver film. But this is just a number that you look up. And this one is just a number that you look up. Which is why we can get to this just being the number that you look up. It's right here. Here you only have to look up one number. And then you get the distance modulus from that. Now, one of the questions in the reading is how do you make a spectra? And I went over that a little bit on Friday, but the basic technique is, oh, did I not put it? It's not in this slide. The basic technique is you take a metal sheet and you cut a slit in it and you put it over your focal plane so it makes a diffraction pattern. And that diffraction pattern spreads the light over a bunch of cells, which is why they're expensive, because you got to put this metal plate in front of your thing so that the only light you see is this little thin slit. But then what do you get? You get a lot of different colors, and that's a lot of work. So taking spectra is great because it gives you a lot of physics, but a headache because you can only kind of do one at a time or a handful at a time. I can't do a whole globular cluster. There's 1,000,000 stars in this globular cluster here, and I want to know what each one of them is so that I can say how the globular cluster is structured, so that I can say what's in the globular cluster, so that I can ask how many times stars have formed. Did all the stars form at once? Did they form? So all these things I can ask if I know what these stars are. So what I want to be able to do is cut out just particular colors. And we come to the, actually I want this other slide deck because it's better. So when I get the thing I want, hey, right there, cool, okay. So for this, what I want, so this is a black body, and it has a specific peak at 2 millimeters over the temperature. So that I can learn what the object is doing, I can learn what the temperature is just by measuring the peak of the black body. But I might not always have that. So sometimes the peak of the black body is in the ultraviolet. And I don't have an ultraviolet telescope because there aren't ultraviolet telescopes, because the ultraviolet doesn't go very far in the atmosphere. You have to put your ultraviolet telescopes in outer space. So that's real expensive. But what I can do is note that the slope of this is directly proportional to the peak as well. So all I need to do is know the slope over here. And what do I need for the slope? I need to take a derivative. It's just rise over run, again. So I just need to measure the flux at 2 different wavelengths, and then I have the slope here, and then I can get what the temperature is, right? And I can do that for all the stars at once by taking filters. So how does a filter work? So here's a spectrum. This is how a spectrum works.
How thin is that slit in all actuality?
Varied.
Very large.
No, it's very thin. So the stars are point sources, so they don't take up any space. So it's probably on the order of the point spread function of the telescope. So they make it just as small as they can. The actual width is going to be set by the diffraction pattern. So if you make a wider slit, you get a wider diffraction pattern. So they tune that to be so that it fits just right. So it's got to be small enough that you get the diffraction pattern, and then big enough so that the diffraction pattern is spread out.
So is it not one size of the slit fits all?
That's right. It's going to be a different slit for every telescope. And some spectrographs don't work like this at all. Some of them scatter the light off of a prism or off of a grating, like a diffraction grating. So there's lots of different ways to actually make them work. I think you can basically say that every telescope has its own spectrograph, except for commodity ones. Oh, sorry, you are in the way. Where did you go? You're on the other desktop. You gotta go because I'm done with you. So we want to do this with colors. So this top line here is the atmospheric transmission in the atmosphere. And you can see that in the visible light right here, there's a lot of transmission. So 1 here means it's clear, it's transparent. As you get to shorter or longer wavelengths, water gets in the way and starts to absorb all this stuff. And I want to break this thing into smaller chunks anyway, because I don't want to measure this whole thing. So we just break it into patches that we call U, B, V, R, I. And there's a whole bunch of different ones. Here's one set. There are different sets that you can define with different colors based on what you need, where specifically you need those filters. But the way these work, and the way the color works, is, I'm going to talk and write at the same time. The way the math works, so we remember to get, I had my monochromatic flux. I have my flux function here. To get the bolometric flux, I integrated the whole thing from 0 to infinity. To get the B magnitude, or to get the B flux, we'll call this F sub B. This is the integral from, let's see, what's the B filter? I have it on here. Let's see. Let's pick a filter. So these are the standard UBVRI filters. So let's say B. So each filter has an effective wavelength and effective width. But so let's just call it 445 minus. That's the width. So I just want half of that. So let's say that this goes from 400 to 490. Okay. So this filter just lets light through between 400 and 490 nanometers and rejects everything else. It's not actually a step function, it's got a shape, but we'll just call it a step function for now. So to get the B flux, I would integrate from 400 nanometers to 490 nanometers of my flux function. Nope, what did I call it? I called it L of some lambda U lambda. Does that make sense?
And
So
what's the top one?
So this is the bolometric. This goes over all the light. B just goes from one frequency to another frequency. Now, this integral is not something that I can actually do with a telescope. What I can do is write down a filter function. We're going to call this T, and it's got some. We'll call this TB, and TB is a step function that turns on at 400 and turns off at 490. And I'm just going to multiply TB by my luminosity and integrate over everything. So my B band flux is then going to be the integral from 0 to infinity now of TB times L lambda, D lambda. So this is the same thing. Just adding this switch, instead of changing my limits of integration, I'm adding this switching function that switches off.
So I'm going from 0 to infinity of that. Now why is that? Because I have to go from 0 to infinity because everything hits my detector. I can't pretend that some things aren't hitting my detector. So we define the B band flux like this, where T is the filter. Now, I drew it here like a step function. Realistically, they're Gaussians, or something close to a Gaussian, but they're very narrow, so it doesn't make a huge difference. So then, how do I define a color in a magnitude sense? I'm on the wrong desktop. Then I define my color here. B minus V. B is the B band flux, and V is the V band flux, which is defined the same, but I use a different filter function in that middle there. And that's going to be minus 2.5 times the F flux, the B band flux over the V band flux. So these fluxes I get like that, and B and V are what I get from this formula. So it's again, so B, here, let me write this a little more clearly over here. So B is going to be minus 2.5 times the log base 10 of So putting all the dingbats in and not waving my hands past anything, the B band flux is going to be minus 2.5, or the B magnitude is going to be minus 2.5 times B flux over the same thing for your fiducial star minus the magnitude for your fiducial star. So these are numbers that you look up. This is the thing that you measure, and this is the thing that you measure. So then when I take two of these, B minus V is going to be, I take this and I take another one that's the same, but with V's. I get minus 2.5 times the log base 10 of FB over FV minus the stuff in the denominator, minus 2.5 times the log of FB0 over FV0 minus MV0, MV0. Okay, all of this crap is just some number that you look up. Or sort out some other way, or I will show you. So, I'm happy saying B minus V is minus 2.5 times the log of B over V. Okay. Anybody have any questions about color? Always oriented so that lower number is more blue. Right, now I'm going to talk about quantum mechanics. These are slightly rough notes. I don't have nice slides yet. So we will go over here. So Astro texts a lot of times start with Kirchhoff's laws, which are cool. They're they're empirical things, and I'm going to write them a little differently, but well, they contact with them. So Kirchhoff said that dense stuff make continuum. So dense stuff makes continuum radiation. Hot diffuse gas produces emission lines, and cold makes absorption lines. So that's what Kirchhoff said. I'm going to generalize that. There's two kinds of radiation that I care about. There's continuum radiation and line radiation. And they tell us different things because they tell us very different processes. So And line radiation can either be in absorption or emission. So you can, the line can absorb things just as well as it can emit things depending on the temperature structure, which we'll talk about. But we got two kinds of radiation. Continuum. And this comes from thermal processes. And it's continuous because the photons are emitted from a range of processes instead of discrete processes. And what does that look like? So if I have a spectrum, this is lambda and this is my flux, that's going to have some distributed shape. So there's light at a whole bunch of frequencies that are spread out. The other kind of radiation that I care about is line radiation. And these, in principle, are infinitely thin and only at one frequency. But that's not actually what happens. They have a spread to them, so there's some width to the line, but it's still predominantly around one frequency. And things close to that frequency, where close to that frequency is set by the temperature of the object. We'll talk about what makes the lines broad in a second. So what we need to talk about is our photons. So why do we have these two kinds of things? So the continuum radiation, this is thermal radiation, and this is black body. It's a black body most of the time. I can come up with lots of examples that aren't, but I'm not going to muddy the water with them because it just gets confusing. So cosmic rays have a continuous spectra that's a power law, not a black body, because they're set by other thermal processes. The continuum radiation from a black hole is set by many black bodies, so it itself doesn't look like a black body, but it is continuum radiation set by a black body. So when you have continuum physics, that sets the continuum background, and when you have quantum mechanics, that sets lines. So why do we have these things? We have these things because we have photons. A photon has one property, two properties. It has an energy, and it has a direction. And that's it. No, that's a lie. There's a wavelength and a direction. There's one free parameter. We'll call it the frequency nu. So the energy is h nu. This is 3 characters, one Einstein, no Nobel Prize. Because this is a weird thing. Because a photon has exactly one specific energy. It doesn't have any other hair on it. The reason that he came to this was for the photoelectric effect. We'll talk about that in a second. So photons have an energy. They also have a momentum, which is E over C. So you gotta kind of just deal with the fact that there's a momentum without mass, because momentum is always mv. There's a better insight that I could have there, but I don't have it on me right now. Give me a minute and I'll come up with one, but I don't have one today. So they have energy, they have momentum. The reason they sorted this out was from the photoelectric effect. So in the photoelectric effect, we have some metal, right? So I got some metal surface. They did it with rings of metal, and they would shine light on the rings of metal and watch electrons jump across a gap in that ring. So if I shine a photon on my metal, so the metal is filled with atoms, and this is really true for, well, the quantum mechanics is always true, but anyway. So if I have a metal, it's got a bunch of atoms in it, and they're arranged in some kind of regular lattice-ish. It doesn't have to be super regular, but there's some collection of protons, of nuclei, and then I've got electrons in a sea around them. These electrons are bound by the Coulomb force to all the protons. And it takes a certain amount of energy, phi, to take one of those electrons off of that lattice. And what they learned was if I have photons with energy phi minus squiggle, so just a little bit less than this function phi, no electrons come off. No matter how many photons I throw at it. So it doesn't matter if I take so if this electron has a work function phi, if I take 1,000 electrons with energy phi over 2, that all adds up to enough energy, but it doesn't actually work. Because each one of those photons goes right past it. Each photon doesn't care. Once the photon has more energy than phi, then the energy of the electron that comes off is h nu minus the work function. So that's the energy that I had from the photon, and this is the energy that I lose to getting off the metal. So this is like an escape velocity kind of idea. So this is the energy of the electron once it's left. But if the photon isn't big enough, it doesn't have enough energy, then no electrons come off. And this was a monumental change in the way we viewed the world. Let's see. I'm going to talk really quick about Compton scattering because I don't really need it. I'll bring it up again if I do.
What does that energy say at the bottom right?
Which?
Bottom right.
E equals h nu minus phi. So this is the energy of the electron that comes off. Okay, Compton scattering. What Compton scattering shows is that you can change the energy of an electron, of a photon. One of the things that comes out of it is sorry, there's a combination of, there it is. So if I have an electron and I have a photon, they can collide and change each other's energies. But they change direction if they do that. So if my electron and my proton hit each other head on, nobody changes energy. They just bounce back the way they came. But if there's an angle, then I can get some change in the energy, and they write it as delta lambda equals, let's see, h bar over m of the electron c, that's the only thing I need that for, 1 minus cosine of the angle. So this is the wavelength shift. So if I have a photon and I hit it with an electron with a certain energy, it's going to change the energy of my photon. It's also going to change the direction of my photon by this much. Those two things change in concert with each other. So where does this formula come from? Remember doing car collisions in 2049 or 2048?
Yeah.
When you did two things running into each other, and you had E1 plus E2 initial equals E1 final plus E2 final, and the momentum P1, and that's a vector initial plus P2 initial, that's also a vector, equals P1 final plus P2 final. And these are vectors. So this is a vector expression, this is a scalar expression, and you have to simultaneously solve these two expressions. And if you do that, this formula comes out. Yeah.
And is that theta the angle that they meet at, incoming?
Both.
It's the
Incoming
same
is
angle?
outgoing.
Okay.
Yeah. By symmetry of the problem, incoming is outgoing.
Okay.
Yeah.
Is it an H bar or a phi?
That's an H bar. It's a very good question. Because if it's a 5, it's not quantum mechanical, but remember that I've got my quantum mechanics residue.
Is that line next to the quantum mechanics residue supposed to be there?
No,
Okay.
that's
Just making sure.
just a scratch. So, okay, I'm going to stop. So Compton is interesting. We don't really need it for a lot. You can see it all over the place. I'm going to come back and start with the Bohr model on Wednesday. So that's what we'll pick up.